In this video, we're just going to do another example of trying to apply the central limit theorem to a problem. So if you'd like, it'd be a good time to try to pause the video and work it on your own first, and then see if our answers match. So we would like to see if exam scores go up on the second exam. That will be useful for us in a little bit. Suppose that the mean exam 1 score was 74.5 points with a standard deviation of 15 points. We take a random sample of 64 students for exam 2 and found their mean score to be 78.8 points. So let's start by just labeling the values that were given to us. So we are given a 74.5, a 15, a 64, and a 78.8. So we need to first start by figuring out what all of these numbers are. So let's maybe start with the easiest one. Usually we recognize that the 64 is going to be our sample size. So that's going to be our N. Then the 15 being our standard deviation, generally it's pretty easy then maybe to recognize that one's going to be sigma. But maybe the hardest two to decide between is the 74.5 and the 78.8 because they're both means. But where they came from is different. It just says suppose that the mean exam 1 score was 74.5 points. Nothing about a sample being taken. So that makes me believe that that's going to be a population mean, or our mu. The 78.8, on the other hand, came from just those 64 students. So it's coming from that sample of students. So that's going to be my sample mean y bar. Now we can dive into actually doing the problem. The first part asks us to find the sampling distribution of the statistic of interest. So first, since I'm working with a quantitative variable of exam score, we're going to check the appropriate conditions. So if I look at my formula sheet or looking back at the central limit theorem, this is what I need. So first, talking about the random sample. Again, it just says that they're taking a random sample of 64 students. So from what I know, they're at least not doing anything in a biased way. Now looking at this OR condition, do we know anything about the exam scores being normally distributed? Well, it does not say that in the problem. I also was not provided a histogram to look at to decide if it looked normal. So from what I know, I can't make the decision that the population is normally distributed. So I need then to have my sample size of at least 30. This one is going to be met for us since our sample size is 64. So all of our conditions are met. So then we're going to be able to say that our sample mean is approximately normally distributed. And again, we need to find its mean and standard deviation. So the mean of y bar is just the population mean itself, which is that 74.5. The standard deviation of y bar is the standard deviation over the square root of n, which will be 15 over the square root of 64, which should give us 1.875. So there is our sampling distribution. In the next part, we're asked, assuming that our exam score 2 mean is the same as the first exam, we're going to find the probability that our mean of 64 students was at least that 78.8 points. So let's start with our picture. So here's our picture. So we've got to figure out what our mean is. The mean is that overall population mean, so it's going to be that 74.5. Now, what standard deviation should we use? It is very easy to make the mistake and try to use the standard deviation of 15. But we're looking at the probably that our mean of the 64 students. So somewhere this 64 needs to be used. That 64 is being used in that standard deviation of our y-bar, or sample mean. So technically my distance here is going to be 1.875 for each value I go out. So we're going to first subtract off that 1.875 each time we move to the left here. And we'll add the 1.875 as we move to the right. So here are our values along the bottom. Now 78.8 is our key number that shows up, which is somewhere roughly about here. And this one says at least at 78.8, so we're going to be shading to the right. Since we're looking at the mean of the 64 students, we're going to be using that Z-score that looks at the mean of n values. So this will be the Z-score formula that I'm going to use. This is where also the picture can be helpful, because I can see that my Z should be between 2 and 3 standard deviations above the mean. So my sample mean is at 78.8. My population mean is the 74.5. And the standard deviation of y bar, that's sigma over the square root of n, is the math we already did up here of that 1.875. Doing our calculation, we should get a z-score of positive 2.29, which is between our 2 and 3 that we could tell by the picture. Taking that value to the table, we should find 0.9890. Since the table reads left and we are shaded right, we will do 1 minus that value to actually get our probability. Finally, interpreting this, I would say, assuming the mean score on exam 2 is the same as on exam 1, that is that mean is 74.5. Then the probability that the mean exam score of 64 students I'm going to specifically make sure I say the exam 2 score, since that's what we measured, is at least a 78.8, is our 0.0110, or what would be 1.1%. So a pretty small chance of happening. But this lends itself well then to think ahead well, what does that really mean for me? At the very beginning of this problem, it said, do exam scores go up on the second exam? So if you really think about what we've just written here, we've really taken the idea and written an alternative hypothesis. I really want to know, well, is the mean higher on exam 2 than it was on exam 1? Well, the mean on exam 1 was 74.5, so I want to see, well, is the mean of exam 2 higher? So I really have this alternative hypothesis that I want to test. And what I've calculated here as my probability is really just a p-value as well. And we've seen those ideas before, not in the same context, but we've seen these ideas. So let's think about what that probability technically was measuring. It was telling us that if nothing changed from exam 1 to exam 2, that is, the mean stayed the same. So the mean on exam 2 is the same as it was on exam 1. Then the probability of our data happening is very unlikely. Right? Only about a 1% chance of happening. So if something is very unlikely to happen, and it does happen, right? So we had it 64 students, their average was a 78.8. That's sort of giving me hope then that the exam scores have gone up. So thus, I believe it has changed, and more specifically, has gone up. Now, why do I think it's gone up? Well, my sample mean that I got was bigger than that exam 1 score mean. So if I was looking at this for students, I would say, it looks like scores do go up on exam 2. At least the mean. I'm not saying every single student's score goes up, but it looks like the mean exam score does go up on exam 2 compared to exam 1. Now this idea is going to lend itself very well into our next module that we're going to discuss confidence intervals and hypothesis testing for a quantitative variable.